As we continue section 13.2, we're going to talk about the third and the strongest intermolecular force, hydrogen bonding. Well, I made that kind of confusing because it's not a bond, it's a force. It is the strongest of the three, and it is only 10% as strong as a, quote, normal bond within a molecule, but it's very, very important, as you will see. Quick recap, you've learned about the first two intermolecular forces. London dispersion forces are the weakest, and they're caused by a temporary shift in the electron clouds on atoms and molecules, creating temporary induced dipoles. Everything has dispersion forces. And the second force, which is medium strength of the three, were the dipole-dipole interactions. Those were permanent dipoles caused by differences in electronegativity, having attractions between the positive and the negative ends of two different molecules. So let's consider hydrogen bonding. Now I'm going to ask you to pause here and go find a worksheet that says amazingly hydrogen bonding. It's going to look something like this when you get done. And this is actually a picture here of the worksheet itself. So pause the vodcast while you go get a pencil and graph the relationship between boiling point and molecular mass for the two sets of data on the two graphs below. And when you come back, we'll discuss the why of how substances behave if they do or do not have hydrogen bonding. So now that you're back, let's take a look at this actual boiling point, not bowling point, typo there. And this is one of the graphs that shows the relationship between the mass of a substance, a compound, and the temperature at which it boils. Remember, the higher the temperature at which something boils, the stronger the forces that hold it together intermolecularly. Now notice that sulfur, selenium, tellurium, and also oxygen lie in the same column or family on the periodic table. And notice on this graph that they are all attached to hydrogen. And actually it goes oxygen at the top of the period or the column, then sulfur, then selenium, then tellurium. As you go down a column, the molar masses increase. You would think that they would have more intermolecular forces caused by bigger electron clouds. That's the London forces. And in fact, these three guys, the compound made with sulfur, selenium, and tellurium, do exactly that. As you go down their column, yes, I know they're negative numbers, but the values for the boiling points get warmer and warmer because tellurium has more electrons than selenium does, which has more than sulfur does. So why, you might ask, would you expect water, which is attached to a hydrogen's attached to oxygen, why isn't water somewhere down here for its boiling point? It's because water can perform hydrogen bonding. And the reason why it can is because of its shape. And why does it have its shape? Because it has unshared electron pairs on the center atom. So you will have graphed something very similar on the corresponding graphs that you see on your worksheet. Let's take a closer look at that. Hydrogen bonding obviously has to involve hydrogen, but it can't be just any other elements. It can only be when hydrogen is bonded to what I call NOF, nitrogen, oxygen, or fluorine. And actually, hydrogen bonding is a special kind of dipole-dipole interaction because water, as you know, is bent. Let's take a look at this picture. All the water molecules are bent or angular, and not shown on this picture is the Y. The oxygen has two unshared pairs of electrons which repel the bonds that have the hydrogens, making water a permanently polar molecule. So the hydrogen bond occurs when a hydrogen on one molecule is attracted to unshared electrons on another molecule nearby, or in the case of giant molecules, it can bend back in on itself. More on that later. This picture, I think, is pretty descriptive. Please make sure you understand the color coding in the slides because your PowerPoint is notes on your handout are printed in black and white. Black dots represent unshared electron pairs. Red dots between two molecules are showing that there's a hydrogen bond. So this hydrogen has a strong attraction to unshared electron pairs on the oxygen nearby. That could be between two water molecules. Or it could also be between two molecules that have hydrogens bonded to N, O, or F only. This hydrogen is attracted to that single pair of unshared electrons on the other ammonia nearby. And finally, you could also have a water molecule that's dissolved some ammonia, and there's hydrogen bonding occurring here. Notice that all three of these bonds that hydrogen can make with nitrogen, oxygen, and fluorine are always polar. So if water didn't have those two unshared pairs of electrons, it would no longer be bent, it would be linear. And life as you know it would not exist. And you and I would not be having this one-way conversation right now. And that's because it's only when you can bend the molecule and make it polar and have that hydrogen attached to an N, O, or an F can you create those very strong hydrogen bonds. Here's another picture of it. Please notice that the solid lines that you see here and here represent the bonds within the water molecule, but the dotted lines represent the hydrogen bonds. Crummy name, it's a misnomer, it's really a force, showing that there are intermolecular forces called hydrogen bonds between two different water molecules. You and I are made up of cells. Inside every single cell is that stuff, DNA. And as you learned in your integrated science class, that DNA has that magical double helical shape where the two strands are able to open up and copy themselves and close back together again in cell replication. Well, you guessed it. Between the base pairs in the center of a DNA strand, they're held together by hydrogen bonding. Very important in these giant molecules like DNA. Another thing that hydrogen bonds are very important for is the three-dimensional structure of proteins. You and I are made up of proteins. We eat proteins. We have proteins acting as chemical messengers throughout our body every nanosecond of the day. Well, what you can have is proteins start with the basic primary structure of amino acids, but then you can bend and fold them into what they call secondary, tertiary, or even quaternary shapes because of hydrogen bonding between two different parts on the same giant molecule. It's kind of important that you have this one down here because the oxygen in your blood is trapped in something called a heme. And it's got a little iron atom in the center of it, and it's got just the right shape for it to pick up this giant molecule, oxygen, from your lungs and bring it to parts of your body where it's supposed to do its work in metabolism. So hydrogen bonding is very important for the folded structure of proteins, as well as the structure of DNA. When you denature a protein, that's like when you cook an egg, when you're frying an egg, you're breaking the hydrogen bonds. And you can see the change in the shape when an egg goes from a clear egg white to a white egg white after you've cooked it, fried it, and broken or denatured those hydrogen bonds. There's another important factor about water that is caused by hydrogen bonding. Water is very unusual. Do ice cubes float? Well, duh, yeah. And water's unusual in that its solid form is less dense than its liquid. That's not very common at all. Ice cubes float. Usually it's the reverse. Solid forms are more dense than the liquid form. Well, the reason why ice floats is because as the water begins to freeze, the water molecules push apart from each other and they take on a different arrangement that's more open. They still have the same hydrogen bonding, but the molecules, as we will see in the next slide, are pushed out. Here's this section of this little snowflake. Here it is expanded, and we're going to focus on just this section here, When you look at the distances between water molecules and solid ice, they're farther apart than they are when they're in liquid water form. They're closer. So since there's less mass per unit of volume, the form of water that's solid, ice, is less dense than liquid. Hydrogen bonding is also very important. As I said, if hydrogen bonding didn't occur in water, water could not exist as a liquid at room temperature. If you go back to this original worksheet, the other three compounds, hydrogen sulfide, selenide, and telluride, those are all gases on the surface of the planet. But water can be a liquid on surface of the Earth temperatures because it has hydrogen bonding. And of course, life evolves and continues to go on because we're all soupy, salty mixtures of water and lots of ions. So life on Earth is possible. Another very important concept that hydrogen bonding contributes to, we'll study later, it gives water a high surface tension. Perhaps you've seen little water striders, insects that seem like they can walk on water. We'll learn how that can occur in another section of the chapter, but that's also due to hydrogen bonding. And finally, water, as you saw when you graphed this worksheet, has a very high boiling point, all a function of the strength of those hydrogen bonds, not bonds, forces, but of the three, it's the strongest. So now you're at the culmination of being able to complete this worksheet. You have two questions on the back of the worksheet. The first question says, describe the trends that you see. And the second question says, account for this trend. So when you're answering these questions, for example, you need to be able to describe why you are seeing an increase in the temperature of boiling from hydrogen sulfide to hydrogen selenide to hydrogen telluride. And I want you to think about their molar masses and the intermolecular force that is a direct function of having bigger molar mass and bigger electron clouds. The same would be true for a trend that would go from hydrogen chloride to hydrogen bromide to hydrogen iodide. Hydrogen iodide should have the highest boiling point because it's the heaviest, and iodine has way more electrons than bromine and chlorine. But be sure to name the force that's accounted for in this example. And that's what you're supposed to be doing here in Part B. However, you also need to be looking at what's going on with H2O and HF that's different than the other elements in their column. Remember, all of these are bonded to hydrogen. And account for and explain why they don't follow the trend. And try to extrapolate and predict what you think the boiling point for those two substances would be. Please be sure to complete the worksheet and turn it in at the time that your teacher assigns it. Thank you, and we will see you at the next podcast.